A gold processor has two sources of gold ore, source A and source B. If you're curious what ore means, it's a naturally occurring solid that they extract to make money. So there's two sources of gold ore. In order to keep this plant running, at least 3 tons of ore must be processed each day. Ore from source A costs $20 per ton to process. Ore from source B, $10 per ton to process. So I'm going to let X be equal to the number of tons from source A, and then I'll let Y be equal to the number of tons from source B, since they refer to tons from each source. It says costs must be kept to less than $80 per day. Moreover, federal regulations require that the amount of ore from source B cannot exceed the amount of source A. If ore from source A yields 2 ounces of gold per ton and ore from source B yields 3 ounces of gold per ton, here's the question: how many tons of ore from both sources must be processed to maximize the amount of gold? So here for my objective function, they're asking for the maximum amount of gold. So here we're going to be maximizing, and I'll let gold be equal to, now here it says in yellow, if ore from source A yields 2 ounces of gold per ton. So since X is the number of tons from source A, here I'm going to have 2X plus, again in yellow, ore from source B yields 3 ounces of gold per ton. So I'm going to let 2X plus 3Y be the objective function. Now for my constraints. Here in blue, it says at least 3 tons of ore must be processed each day. So if I take the tons from source A, which is X, add that to the tons from source B, that's Y, it must be at least 3. So at least in math is bigger than or equal to, in this case, 3. So that's the constraint that deals with the amount. Then it looks like we have some costs going on up there in red. It says the ore from source A costs $20 per ton to process. So that's going to be 20 times X. And ore from source B costs $10 a ton, so that's going to be 10Y. Costs must be kept to less than $80 per day. Okay, so that's my second constraint dealing with the costs. Now we have this in green. It says federal regulations require that the amount of ore from source B. Well, I'm going to kind of translate this verbatim here. The amount of ore from source B. Well, that's Y. It says cannot exceed, so cannot be bigger than, which means it has to be less than or equal to twice the amount of ore from source A. So that's going to be 2X. So that's going to be the constraint I'm writing based on the federal regulations. How many tons of ore from both sources must be processed to maximize? Here, I'm going to also throw in the fact that you can't have a negative amount of tons of gold ore, so I'm going to go X is bigger than or equal to 0, Y is bigger than or equal to 0, and I claim this is how this problem should have been set up. Now if you want to see what the solution area looks like, you can pause the video, and then I'll put up on the screen here what your solution area should be. Okay, here is my solution area. What I did was I went to zoom and I chose option A for zoom quadrant 1, this is one of the things you can do if you know that both x and y have to be bigger than or equal to 0. Sometimes, though, this can make it difficult seeing the vertices that lie on the x and y axis. So sometimes it might be in your best interest just to keep a little negative area for your x min and your y min, so it kind of moves the graph up. But here it looks like you should have a solution area that looks like this, and there should be 4 vertices. So here your 4 vertices should be 3, 0, 1, 2, 4, 0, and 2, 4. Now what we're going to do is we're going to take each of these points, each of the points has an x and a y value. We're going to plug them all into this objective function, this gold equation, and see which gives you the largest value. So here, to maximize the amount of gold, they should extract 2 tons from source A and 4 tons from source B. And here the maximum amount of gold is 16 ounces. Problem 2, a small town is trying to establish a transportation system of large and small vans. It can spend no more than $100,000 for purchasing both vans and no more than $500 per month for maintenance. A town can purchase a small van for $10,000 and maintain it for $100 a month. Large vans cost $20,000 each and can be maintained for $75 per month. Each large van carries 15 passengers, small van 7 passengers. Here, find the maximum number of passengers. So here I know my objective function. Before I even write my let statements, my objective function should be a maximum, and here I'm going to try to calculate the number of passengers. Question says how many large vans and how many small vans will they need. So here I'm going to let x be equal to the number of large vans, and I'll let y be equal to the number of small vans. It doesn't matter if you let x be equal to the large and y be equal to the small, or vice versa, as long as you stay consistent. Now the objective function deals with the number of passengers, and that's what I have going on here in green. Each large van carries a maximum of 15 passengers. So I'll take 15 and multiply that by x, the number of large vans. And then each small van carries a maximum of 7 passengers, so I'll let 7y be equal to that. So here's my objective function that I'm trying to maximize. Now for the constraints, so here it says they can spend no more than $100,000 for purchasing. So no more than means less than or equal to. So here I'm going to write a constraint dealing with the spending, and it says a town can purchase a small van for $10,000. So y is the number of small vans, so I'm going to go 10,000 y, And then it says they can purchase a large van for $20,000. And since X stands for the number of large vans, that's going to be 20,000X. So that's my constraint dealing with spending. Then they talk about maintaining these particular vans. It says they can spend no more than $500 per month for maintenance. So again, no more than is less than or equal to 500. Small vans maintain for 100 a month. So I'm going to go 100 times Y, the number of small vans. It says large vans can be maintained for 75. So that's going to be 75 times X. Here they tell you the maximum number of passengers. That was my objective function. And here it looks like the only two constraints that we need to add are the minimum value constraints that X and Y both can't be negative, so bigger than or equal to 0. So here are the constraints that you should have written. And I'll put up on the screen in a minute the viewing window and the solution area. So here for my viewing window, I went from -1 to 7 for both the X and the Y axis. By making the X min and the Y min -1, it kind of gives you some space underneath the X axis to the left of the Y axis. It allows you to see the vertices that lie along the X and Y axis a little bit clearer. So here we have 4 vertices for this problem. And here the vertices should be 4, 2, 5, 0, 0, 5, and the origin 0, 0. So we're going to take each of these vertices and plug them back into this objective function, the passengers, and see which one gives the maximum number of passengers. Each of these points has an X and a Y value. So here it looks like the vertex 5, 0 maximizes the number of passengers. So here the town should purchase X, which is the number of large vans, so 5 large vans, and 0 small vans. And the maximum passengers is equal to 75. So there's our official final answer.